All right, so section chapter 5, section 1, we will start with the starting section 1, which is about the magnetic fields. Chapter 5 is defining the magnetic fields uh, of a natural magnet first. After that, we will define the magnetic field of current carrying wires. And then in section 3, we will define the effect of magnetic field on charged particles and the wires, which is moving inside a magnetic field or located inside a magnetic field. So the first section 1, so we will first try to understand what is the origin of magnetic field. And every field concept is used first to explain the interaction of two non-contact objects. And for example, gravitational field is explains the how two non-contact uh, masses in the space interact with each other. Or electric field defines or explains how two electric charges which is not in contact can interact or repel each other. A field concept is also the same way. It also explains the interaction between two non-contact materials like a magnet and another magnet, or like a magnet and an iron. How do they interact with one another? So two non-contact forces are also named as field forces. So the first field force, as I said, is the gravitational force, which is static. Second field force is the electric field, which is or electrostatic force between the charged particles, which are at rest. And the third field force is the magnetic field, which is produced by charges in motion. So the difference between these two is that so charges in electric field is produced by electric charges which are at rest, they don't move, but magnetic fields are produced by electric charges which are in motion. So what is in motion in a magnet, or what is in motion in a substance? Of course, electrons are in motion. So electrons are moving inside a substance, and then they have two types of motion. One of them is electrons are revolving around around the nucleus. One of them is this. So because of this revolution around the nucleus, this electron some kind of traits like a kind of very tiny magnet. Second motion is electrons are spinning about their own axis, so rotating about their own axis. These two motions of electrons, these two types of motion of electrons, provide a magnetic field for each atom. In fact, there are many electrons which is moving around the nucleus. All these combined, and then because of this motion of electrons around the nucleus of the atom, so every atom or many atom, most atom behaves like very tiny small magnets with N pole and S pole. Uh, but there are billions of atoms inside a substance. Uh, if these atoms are magnetic fields of atoms whose or groups of atoms whose magnetic fields are parallel or in the same direction, forms a domain. So look at one atom, second atom, third atom. So as you see, their magnetic fields are in the same direction. Uh, Another groups of atoms whose magnetic fields are parallel but different than the first one. This is another domain. So third group of atom whose magnetic fields are also again parallel but different than the first and second. This is also another third domain. So they form domains inside a substance. As I said, billions of atoms, all they have the same directed magnetic fields. And after that, these domains, again, could be billions of magnetic domains in an atom. So if all these domains or most of these domains are in the same direction, so this is one of the group of atoms, one domain, this is another domain, this is another domain. So as you see, domains are here in the same direction. If most of the domains in a substance are in the same direction, so that substance, it becomes a natural magnet. So this substance is a natural magnet. But if the domains are in random directions like this one, so they cancel out. So for example, this one and that one almost opposite in direction. So um, this one and that one, this one and let's choose another one, uh, this one and that one in opposite direction. So then billions of them are in opposite directions. So they cancel out. The net magnetic field becomes zero. So this is not a magnet. This is a material, magnetic material, which is called iron, nickel, and cobalt, which can be easily attracted by a magnet. But magnetic material. Magnetic material doesn't mean that it's a magnet. Magnetic material means which is attracted by or affected by a magnet. Third group is no domains, as you see here. Only domains are the magnets, atoms have their own magnetic fields, no domains, and they cancel the effect of one another at them, but no domains. If no domains are formed, it is not a non-magnetic material like rubber, like paper, like plastic, and so on. And when a magnetic material such as an iron is exposed to a natural magnet, so this is the magnetic material, as I said, there are domains in random directions and then they cancel with each other. It's an iron. But if you keep a magnet close to this magnetic material, direction of the iron domains of direction of the domains are changing. As you see, it was randomly arranged here before exposing a magnet, but after exposing a magnet, so all these domains becomes in the same direction. So if the domains are in the same direction, which means this material, this iron, is trading like a magnet. So before exposing and after exposing, as I said, randomly arranged domains after exposing a magnet, so becomes regularly arranged as happened here. So then iron becomes a magnet, and then it starts attracting to other materials like pins. So a magnet can attract a pin. So pin becomes a magnet. It attracts another pin. So this uh, pin becomes a magnet and it attracts another pin, as you see. So then reason is what? This magnet, that external magnet, is making the domains of this material, magnetic material, this iron, to be aligned in the same direction and a kind of magnet. So this pin becomes. When an external magnetic field is removed, if you take this magnet, which is natural magnet, away from these pins, so the magnetic material retains its magnetization for some time. So then this pin does not lose its magnetic property quickly. So it takes some time to lose its magnetic property. So this event and keeping the magnetism of a material, of a magnetic material after exposing a magnet is known as magnetic hysteresis. And a sectionary problem: when a bar magnet is broken into two pieces, how many poles would each piece have? Of course, so because when you break it into two, still each piece has domains. If they have domains, which means they have magnetic property. So that's why both will have n pole and s pole. There will be an s for one first piece and then s second piece. But what happens? So because you break a magnet into two, number of domains here in when it is not broken, it's a greater number of domains it has, so it was a stronger magnet. But then when you break them, because each piece will have a smaller number of domains compared to the before breaking, so then they will have weak magnets compared to the first one. So the only thing is their strength is changing after you break a magnet into two. And this is now we are going to talk about or show about the pattern of magnetic field around a magnet. How do they form? So a magnet is composed of domains. We know about the domains have n pole and s pole. A magnet also has n pole and s pole, just like a domain. So when some iron filings are spread around the magnet, they are aligned in the direction of the magnetic field lines and form patterns. So here is I think this is a movie about how magnetic irons are aligned around the magnet. When you make iron closer to iron filings closer to a magnet, as you see, iron filings are making the lines around this magnet. So these lines are representing the magnetic fields around this natural bar magnets. So if you carefully look at that, so at the poles lines are closer, which means if lines are closer, so which means that the magnetic field is stronger at the poles here, and then here it is stronger. But you see the traces starting from one pole and then ending to the other pole, and then starting from one pole and going to other pole. So uh, these are also representing the magnetic field lines around this natural magnet. And so then if we make a model for magnetic field lines, so this trace in the pattern represent magnetic field lines, and then model is going to be like this. So line seems to start from one pole and seems to end at another pole, but in fact it is not. So these lines are forming closed paths. Magnetic field lines of the magnet continue their path within the magnet and form closed loops. For that, as in they have no end and they have no beginning. So then, if it is like this, uh, even when we look at this figure, we cannot see that exactly they have a direction. But because a magnetic field is a vector quantity, we should give the magnetic field a direction conventionally. So, and direction of the magnetic field is assumed to be from North Pole to the South Pole outside. It's leaving from North and entering to South in outside of the magnet, but from South, continue from South to North within the magnet. So this direction is conventionally given, as I said, normally. When you look at the magnetic field lines, you don't see a direction, but mathematically we have to give a direction to magnetic field because it's a vector quantity. And compass needle is also a tiny magnet with N pole and S pole, so it is used to find the direction of the magnetic field at any given point in any space around you or around a magnet. Okay, compass needle never stays at some angle to an external magnetic field. So as I said, compass needle is also a magnet with N pole and S pole. So magnetic field within the magnet is from S to N, but outside from N to S, it's going this way. But if you put a compass needle compass inside an external magnetic field, this magnetic field can be a magnetic field of a bar magnet, or can be magnetic field of a wire, or can be Earth's magnetic field. If you put a compass needle inside a magnetic field, external magnet, it will rotate until needle's magnetic field and external magnetic field becomes parallel and in the same direction. When just look at this figure, in this figure magnetic fields are not in the same direction. Compass needle's magnetic field is blue, which is in that direction, but external magnetic field, let's say that it's the Earth's magnetic field, is to the right. So this needle will start rotating until spinning until both magnetic fields, which is the needle's magnetic field and the Earth's magnetic field, becomes in the same direction. That's why North Pole, which is generally represented by N, North Pole of a needle always points direction of the magnetic field at that point. So direction of the external magnetic field is from left to right. So North Pole, which is red, is also pointing from right to left. It's pointing to the left. So that's why we said that yes, compass, N pole of a compass always points the direction of the external magnetic field at that point. So N pole of a compass needle always points in the direction of the magnetic field at that point. Okay, now this is a natural magnet. So we put 10 or magnets, several magnets around this natural magnet. So then several compasses. Sorry, so we put several compasses around this natural magnet. This each compass must point in the same direction of the magnetic field of this natural magnet. So then This shows that magnetic field lines are pointing in the same direction of these red ends. So here magnetic field must be in that direction. Here it must be to the right. Here must be to the right. Here must be a little curve to the magnet. Here must be changing direction to the S pole. Here must be directly S pole. So this shows that magnetic field lines are leaving from N to also entering to S. Leaving from N and entering to S. So direction of each compass needle points what the direction of the external magnetic field is at that point. And one of the sectionary question, which of the compass needle orientation in the figure might correctly describe the magnetic field at that point. So we know that magnetic field lines are leaving from N and entering to S, leaving from N and entering to S, like this one. So of course, compass needle, which is this arrow, must point in the same direction of the magnetic field. Now, if I look at them in one by one, so in A, it is almost these arrows are showing the same direction. So A could be a possible answer. Let's look at B. B, direction of the magnetic field is from N to S, and the compass is also pointing to in the same direction of this magnetic field. B is a also possible answer. C, but C is not a possible answer because magnetic field is to the left, but compass needle is showing perpendicular to magnetic field. This is impossible, so it must turn until it comes in the same direction. D is almost in opposite direction, so magnetic field here is in that direction, but compass needle is opposite. And then for E, also not in the same direction. For F, completely opposite in direction. So A and B is possible answer. So compass needles are pointing in the same direction of the magnetic field, but C, D, E, and F, compass needle is pointing in the opposite direction of magnetic field of this external magnet. And magnetic field is a vector quantity. Yes, it's a vector quantity. It shows a direction, and then its symbol is B, represented by B, and unit of magnetic field is Tesla, name given after one of the famous scientists, which is Nikola Tesla. And magnetic field is stronger or more intense where magnetic field lines are closer, weaker or less intense at points where the magnetic field lines are farther. Now, if you look at the magnetic field pattern around this bar magnet, you see that they are closer at the poles, but farther when you are moving away the poles. So I choose 3 points here, A, B, and C. If you see that magnetic field is strongest at the A, which is the pole, which is magnetic field lines are very close each other, and weaker at B, but weakest at C. C is very far, so which means when you move away from or go away from the so magnetic field intensity decreases, and then effect of the magnet at that point is less than other points, which is closer. And because it's a vector quantity, we should show the direction of magnetic field. So we will talk about the directions right now. How can we represent magnetic field direction according to the page? So we are going to have magnetic field. If magnetic field is in the plane of the page, which means parallel to the plane of the page. In the plane of the page is one example. So first we should know that there will be two planes, which is one of them is horizontal plane. Horizontal plane is the plane of your page or your book is horizontal because it's on a table. Table is a horizontal plane, but vertical plane is a wall, for example. Wall is a vertical plane. So if the magnetic field is in the plane of the page, means the magnetic field will be on the table, along the table. So along your book or along your notebook. So in this case, we are going to define the magnetic field directions up to the plane of the page. So if the up goes like this, or down to the plane of the page goes like this. So to the right of the page, to the left of the page. So these are when the magnetic field is in the plane of the page. But sometimes magnetic field can be in vertical plane, like the wall, along the wall. If it is along the wall, up to the sky, or down to the ground, it will be like this. So up to the sky is known as out of page. It is coming out from your page, or into the ground, which is represented by into the page, so which is going into. If it is into, It's like an arrow. It's moving away from you. That's why we represent it by cross. If it is out, so we represent it by dot. It's coming, the tip of the arrow. It's approaching to you. So out of the page is dot, into the page is cross. And uh, and one more quantity we will define in this section, which is known as the magnetic flux. Magnetic flux normally will be explained or used in section chapter 6 mostly, but defined here. Its definition is like this. The total number of magnetic field lines that crosses a given area is called magnetic flux. Its symbol is phi and unit is Weber. So this is an area. There are so many magnetic field lines. This area can be a book, or you can hold any shape of the across a magnetic field. Then you will count how many lines are crossing through this area. So if you cross the number of lines crossing this area, so you calculate it, you measure the magnetic flux through this area. So if I count them one by one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 lines crosses this area, which is magnetic flux through this area is 11. So we only care about uh, how many lines are crossing area. This is the only thing about the magnetic flux. But magnetic flux also changes by some quantities. One of them is magnetic field intensity. So right here, I choose identical areas. So this area and that area are equal, so in size, but one magnetic field is more intense than the other one. The one on the left is more intense because they are closer. Lines are closer, much closer to each other. The one on the right is less intense because lines are farther from each other. So more intense magnetic field, in this case, will produce a greater magnetic fields in equal areas. So that's why if magnetic field is increases, and then yes, which means the magnetic flux through the area also increases. So magnetic flux is proportional to magnetic field intensity. Second one is area of the surface, and I choose here equal magnetic field intensity. So here and here, the separation between the lines are equal, which means I choose equal magnetic field intensity for both area. But one area is larger than the other one. So A1 is larger than A2. That's why magnetic field lines crossing this area, A1 is greater than A2. So 1, 2, 3, 4, 5, 6, 7 lines are crossing A1, but 1, 2, 3, 4 lines are crossing A2, which means yes, if you make the area larger, or if you use a larger area, it is possible to get a larger or greater magnetic flux through that area. So magnetic flux is also proportional to area of the surface. And third quantity is the orientation of the surface with respect to magnetic field lines. So I choose equal areas, yes, and equal magnetic fields, yes. But in one of them, here, the area is kept perpendicular to the magnetic field lines. When the surface is perpendicular to the magnetic field lines, so then so many lines are crossing this area. But if you keep an area parallel to the magnetic field lines, almost no lines crosses the area. So which means the magnetic flux, the maximum number of magnetic field lines crosses the area of the surface. So when you hold the area perpendicular to the magnetic field lines, so magnetic flux max becomes maximum and calculated by A times B. So, but in here, in the second one in B, no magnetic field line crosses the areas of the surface. That's why magnetic flux becomes 0 here, and that's why it's going to be written as 0. What if there is an angle between the area and the magnetic field lines? When the surface makes an angle, tilt or inclined to the magnetic field lines. In this case, so magnetic flux will be less than maximum, so it's going to be less than this, but it will be greater than 0, so it will be greater than this. So it will be between these two values, between 0 and maximum. So we can calculate the magnetic flux by an equation. So A times B times cosine theta. This cosine theta. Theta is the angle between magnetic field lines, which is the green lines, and normal of the surface. So we are going to draw a normal to the surface. Normal line is the perpendicular line to the surface. And we are going to get the angle between this normal and magnetic field lines. And area is a vector quantity. Maybe the first time you heard about this in physics. It's a vector quantity because area has a direction. Normal line is representing direction of this area. For example, there's a box. This box has different sides. Each side, area of each side is a different vector. This side is pointing to the right. Normal is pointing to the right. Above side is pointing the up, which is the direction of the area is up. This side is pointing to us. So every different side is pointing in a different direction. So that's why their normals are different. So that's why area is assumed to be a vector quantity. So area is a vector quantity whose direction is the normal of the surface. Sometimes normal, in fact, means perpendicular line to surface. Normal means this. And whose magnitude is the measure of this area. How many meters square or centimeters square this area is? It is the magnitude of this area. Or how many meters square or centimeters square this area is? It is the magnitude of this area, and so on. That's why magnetic flux can be also expressed by scalar product of two vectors. One of them is the area vector, the other one is magnetic field vector. This is just a representation, but we are not going to make any calculation with this one. So you will learn when you go to the university about the scalar products more detailed. And this is all about section 1. I will continue with section 2. Section 2, now we skip the natural magnets because natural magnets produces the magnetic field lines from the moving electrons inside an atom. And the second section was about the current. So origin of magnetic field was the electrons in the motion inside an atom, and these electrons motion is producing magnetic fields around the natural magnet. Remember, we learned that. What about the electrons? If electrons are moving through a conductor, so this is a wire. If you give electric current to this wire, so these electrons are also in motion, so they could also produce a magnetic field around the wire. So yes, they will. So the first scientist who represented this, or who did this experiment, who represented the magnetic field and electric current relation is Ørsted. He discovered the relation between the electric current and magnetic field. He gave a very strong current to a wire, and after that he observed that some compasses around this wire align themselves in the direction, in a specific direction, forming a circle. So then he said that yes, every current carrying wire produces a magnetic field around, so in the shape of concentric circles. And a strong, steady, constant current produces a magnetic field lines around a wire. These magnetic field lines form concentric circles. This is the current carrying wire, as you see, around maybe billions of circles. Billions of circular magnetic field lines form everywhere, not only on one plane. Here, 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 around the wire, everywhere, there are concentric circles. The plane of the magnetic field lines is perpendicular to the wire, so the electric current. Here is the electric current is up to the plane of the page. So in this case, magnetic field must be in horizontal plane if the electric current is in vertical plane. So horizontal plane, magnetic field lines. If electric current is in horizontal plane, so magnetic field lines must be in vertical plane. Yani şöyle düşün. Electric current is moving on the wall up to the ceiling. So electromagnetic field lines must be in horizontal plane on the ground. If electric current is moving on the ground, so the magnetic field lines must be on vertical plane on the wall. So plane of the magnetic field lines, if horizontal, electric current is vertical. If plane of the magnetic field lines are vertical, electric current must be in horizontal. And next one is how to find the direction. So that we know that there are concentric circles, but we know that magnetic field is a vector quantity. That's why we should also give some directions to these concentric circles. So this direction is can be found by right hand rule. We are going to show the thumb in the direction of the electric current. Curled forefinger will represent direction of the circulation of these magnetic field lines around this wire. So when electric current is perpendicular to the plane of the page, so it is like this dot, it's coming from the page out. So if you curl your, use your right hand rule, if you show the thumb is out of your page, you will see that your curled forefinger is rotating clockwise. And so the circulation of the, so counterclockwise, circulation of the magnetic field will be counterclockwise for a current which is out of the page. But if the current is into the page, into your book, into your table, in this case, if you show your thumb into your table or into your page, curled forefinger will represent in the direction circulation of the magnetic field will be clockwise. So this is the beginning of the direction of the magnetic field, but there are some other ways. This is when the magnetic field electric current is perpendicular to the plane of the page. What if the current is in the plane of the page, parallel to your page, parallel to your book, parallel to the your table? So the first one is if the electric current is up to the plane of your page. So if you show thumb, if you show thumb in the direction of this electric current, you are going to see that your fingertips are pointing out of the page on the left side. If you continue curling your hand, right hand, you will see that magnetic field is pointing into the page on the right side of the wire. So on one side it is out of the page, on other side it is into the page. If you change electric current direction, so if the current goes down to the plane of the page, magnetic field direction also changes. Yeah, this is one thing you should always remember. Electric current direction and magnetic field direction, they are dependent. If you change the electric current direction, you will change the magnetic field direction too. So if electric current is down to the plane of the page, if you curl your finger, you will see that magnetic field is on the left side into the page, on the right side of the wire, it is out of the page. And if the electric current is to the right of the page or to the left of the page, again, you are going to use right hand rule. If you curl your thumb, if you hold your thumb to the right of the page, you will see that above the page, fingertips are pointing out of the page. If you continue curling your forefinger, you will see that below the page, magnetic field becomes into the page. Or if the electric current is to the left of the page, and then if you shove thumb in the direction of the electric current, you will see that your thumb is forefinger is pointing into the page, but below the wire it is out of the page. And don't forget, oh, if on one side it is into the page, other side out of the page. If here is out of the page, here is into the page. So this is the case when the electric current is in the plane of the page, when it is in horizontal, up, down, right, and left. So note that when the electric current direction is reversed, magnetic field direction also reversed. And we know how circulation of magnetic field is, but we didn't talk about exact vector direction at different points, because for every point on this circle, direction of the magnetic field is different. For example, here is to the right, here is to the down, here is to the left, here is the up. So for every point on this circle, magnetic field direction, magnetic field vector shows in a different direction. So direction of the magnetic field vector at a point at a distance t from a wire. So this is a magnetic electric current which is into the page I. So circulation of the magnetic field lines are clockwise around this wire. When a compass are located around a current carrying wire, all compass needle deflects in direction tangent to the concentric circles. Yani these tangent lines around the concentric circles points the direction of the magnetic field at that point. For example, at this point, if you want to find the direction of the magnetic field vector, you should draw a tangent line and this tangent line will show the direction of the magnetic field here. And for this point, if you want to find the direction of the magnetic field vector, you should draw a tangent line. So this tangent line will show what the direction of the magnetic vector is here. And here also another. So every different point here will have a different directed magnetic field vector. So that's why when you put a compass on this line of magnetic field lines, all compass will show a different direction. When you combine them all, it's going to form a circle. And direction of the magnetic field at two symmetric points with respect to the wire are always in opposite direction. So this is the wire which is into the page, carrying a current into the page. But magnetic field lines are circulating clockwise here. Look at these two directions. So according to this wire, this point and that point are symmetric. If one of them is in this direction, other magnetic field will be opposite of that one. Here, uh, this magnetic field here up to the at that point is to the right, but here it is to the left. This point is up, magnetic field vector is up, but symmetric point is down. So as you see, in opposite sides or opposite points of a wire, direction of the magnetic fields are on opposite directions. And the magnitude, this is the wire which carries a current I, and on this circular magnetic field lines, every point K, L, M are at the same distance from the wire, which means magnitude of the magnetic field at K, at L, at M, S, N, whatever. So every point on this concentric circle will have the same magnitude of magnetic field, and this magnitude of the magnetic field intensity is calculated by mu over 2 pi iota over d. So mu is the magnetic permeability, depends on the medium. So generally air is the medium for our life. So air has a magnetic permeability which is 4 pi times 10 to the power negative 7. It is mostly given in questions. So I is the electric current. If you increase the electric current, so the magnetic field increases. If you decrease the electric current, magnetic field decreases. Magnetic field around a current loop is the second title. For a straight wire, this is a straight wire, and if electric current is given to a straight wire, so magnetic field lines are circular. They form concentric circles around. All these are representing the magnetic field lines around the straight wire. But if this wire is bent to a loop, if we make from this straight wire a loop like this one. So as you see, when we bent this straight wire into a loop, the magnetic field lines are again concentric around the wire, but at the center, inside the wire, these wires are getting closer. Pardon, these circles are getting closer. These magnetic field lines are getting closer. If lines are getting closer, which means magnetic field intensity is increasing. That's why inside the loop, magnetic field intensity increases, but outside the loop, magnetic field intensity decreases. In fact, it's a kind of conservation of energy. We are carrying some magnetic field from outside to inside, and we are making the inside loop, the magnetic field, more stronger than outside. So that's why we will calculate the magnetic field intensity at the center, which is the maximum. This is the greatest magnetic field intensity of a loop. So intensity of the magnetic field at the center of the singular loop is calculated by equation mu I over 2r. You only remove pi. Pi is not included in this equation compared to straight wire. Instead of t, you are going to write r. Why? Because wire is at the distance of r to the center. Wire is at the distance of r to the center. Wire is a distance of r to the center. Instead of t, you are going to write here r, and you are going to get the equation mu I over 2r for current loop, single loop. Directional magnetic field is at the center, also can be used by using right hand rule. Uh, but this time you are going to make your forefinger, it's better to use this one as electric current direction. Forefinger is representing electric current direction on the loop. Here it's the counterclockwise, for example. So if you make your forefinger on your page counterclockwise, so you will see that your thumb is pointing out of the page, which is representing magnetic field. So this is the easiest one and the most practical way for finding the magnetic field direction at the center of the circular loop. And even this loop has N pole and S pole. So, and thumb is also pointing where N pole is. So here will be N pole. This above the loop will be N pole. Below the loop will be S pole for this single loop. And magnetic field of a current loop similar to the magnetic field of a bar magnet. So remember, bar magnet was also has N pole and S pole. So current loop, this is a loop, also has N pole and S pole. But if there are more than one loop, so if two loops or three loops, you are going to multiply the equation by n. So number of n is representing number of loops. So magnitude of the magnetic field at the center of a circular coil. If there are more than one loops, so this is called general coil. So this is a coil. There are n turns for this coil, whose radius r, and current given to this coil is I, and the number of turns is n. So magnetic field is going to be mu I n over 2r. This is a video how magnetic field lines formed around coil. It's explaining that. So let's see once. Okay, so these are iron filings. As you see, iron filings are in all randomly arranged. They have no pattern. But when electric current is given to this coil, you see that these iron filings align is also a kind of composite, but also has ample. So you find each direction with no result. Said the compass needle is a kind of magnet, so then compass needle can never stay at some angles to the external magnetic field, so it becomes parallel in the same direction of the magnetic field, so then not to tend to rotate. So then if you locate a loop inside a magnetic field freely rotating so that it can freely rotate, it will tend to rotate until its magnetic field becomes in the same direction of this external magnetic field. Then, so at this orientation, when the loop's magnetic field is parallel to the external magnetic field, which means plane of the loop is perpendicular to the magnetic field, so it will rotate. But when the plane of the loop becomes perpendicular to external magnetic field, so it will not tend to rotate. And next one is the solenoid. Solenoid is another important device which can produce magnetic field by current carrying wire. So a solenoid, definition of the solenoid is a wire coiled into successive loops is called a solenoid. So it's a coil, but not so close. As you see, you make this coil longer than the others. I mean, just loops. So solenoid has a length too. So magnetic field around this magnetic field of the solenoid is different than magnetic field of just loops. So inside the solenoid, if you look at very carefully, you will see that the magnetic field lines are almost parallel. So which says that magnetic field inside the solenoid is uniform, which means same intensity at every point inside the solenoid, it has the same intensity because lines are almost parallel. It has a very intense magnetic field, strong magnetic field inside. But outside, it is non-uniform, and different intensity at different point, and weak, very weak magnetic field outside the solenoid because lines are farther. This is a solenoid, how solenoid can produce a magnetic field. This is what we're talking about. As soon as current goes in this direction of the magnetic field, perpendicular to zero. So calculating magnetic field within the solenoid is of course, the equation must include electric current, because if you increase the electric current, magnetic field of the solenoid increases directly proportional to current. If you use more current, which is the number of turns n, so you can also get magnetic field intensity, but inverse proportional to length of the solenoid. If you make a solenoid longer, have magnetic field intensity decrease, and this is the equation for magnetic field intensity inside a solenoid. But sometimes we can rewrite this equation in this form: I n over L. As separated from mu times and mu times I or L is called number of loops or number of turns per length. So yes, B is proportional to N. Yes, P is inverse proportional to length, but B is proportional to N over L. Yani is proportional to number of loops per length. If per length N over L is smaller. Yani if the loops are or turns are farther, which N over L is smaller, we get less intense magnetic field. If you make this looks closer like this one, and over L becomes greater. Greater than over L means more intense magnetic field. And next one is about using a different medium, mu. Mu is also affecting the magnetic field. So mu is magnetic permeability, and it depends on the medium. Air has a very small, weak number of magnetic permeability. But if you use a substance which has a greater magnetic permeability, like iron, and if you insert inside this door or inside this solenoid, you are going to increase the magnetic field intensity. Inserting an iron rod through the center coil increases magnetic permeability. This device is called electromagnet, because this device will have a much stronger magnetic field than the device of the iron coil. And direction of the magnetic field within the solenoid also used by right-hand rule. So your force-field curl in the direction of the electric on this wire, on the solenoid's wire, thumb is going to show what direction of the magnetic field is within this solenoid. Thumb is pointing to the left, so the magnetic field within the solenoid is to the left. And also this thumb is pointing to the end of this solenoid end. So this plus is going to be as for this solenoid. And Earth's magnetic field is last thing. Earth's magnetic field, you know one thing about Earth's magnetic field. This is enough. Earth's magnetic field is from South Pole to North Pole, opposite of a natural magnet. Because we define the Earth's poles not according to magnetic field, according to geography. So Earth's magnetic field starts from geographic south, from Antarctica, and to the geographic north, which is Siberia. Don't forget this. This is enough about this section. I will continue with section 3, which is about charges inside a magnetic field, section 3. And let's choose this, start the section 3. All right, section 3. Let's show the screen. Yes, there are two types of fields. We have one of them is the electric field, the other one is magnetic field. Electric field is studied in the 11th grade. If you locate a charged particle inside the electric field, for example, a negatively charged electron or a positively charged proton, if you locate inside an electric field, this electric field sets these charges into motion. So then this electron starts moving in the opposite direction of the electric field. So electric field, if it is up to the plane of the page, so this electron will move in the opposite direction, which is down to the plane of the page. It will start moving, because electric field always acts a force on a charge which is inside a magnetic field, inside this electric field. But magnetic field is not like this. If you put the same charge inside a magnetic field, so you know this is a bar magnet, the bar magnet has a magnetic field around. If you put an electron at rest inside this magnetic field, so there will be no force acting on this charged particle. So magnetic field cannot set the charged particle into motion. So no, because no magnetic force acts on a stationary charge in a magnetic field. So we will start with this. If a charge is located at rest inside a magnetic field, this charge will not start moving because there will be no magnetic force acting on this charge. And when velocity of the charge is zero, magnetic force acting on the charge will be zero. But if you move a charge inside a magnetic field, so in this case, a magnetic force can act on the charge. So then we say that yes, if a magnetic force may act on a charge in a magnetic field if charge is in motion. We said may because there are some conditions too. So first I'm going to get the equation for calculating magnetic field. The magnet of the magnetic field, Bf magnetic, acting on a moving charge, velocity v. Charge has a Q, symbol Q. In a magnetic field B is calculated by, you are going to multiply all these three, V, Q, and B, and you will get the magnetic force. So it's going to be QVB. Only we have to add an angle. Angle between the velocity vector, direction of the motion, and magnetic field lines. If this angle is theta, so your equation for calculating magnetic force will be QVB sine theta. So theta is the angle between the magnetic field and velocity vector, or between the magnetic field and direction of motion of the charge. So according to angle, yes, this angle, force can change. According to equation QVB sine theta, if charge moves perpendicular to the magnetic field lines like this, magnetic field is to the right, but charge is moving perpendicular, up to the plane of the page. So angle between the velocity and the magnetic field is 90, and sine 90 is 1. So that's why this charge will experience the maximum magnetic force. Maximum magnetic force acts on the charge if it is moving perpendicular to magnetic field lines. And second one, each charge moves parallel to magnetic field lines. So parallel means the charge can move in the same direction of the magnetic field, so which means angle between these two vectors 0, or charge can move in the opposite direction of the magnetic field, which means angle between these two vectors will be 180. In this case, both 0 degrees and 180 degrees is sign. So then we can say that magnetic force acting on the charge in a magnetic field is 0 if charge moves parallel to magnetic field lines. So if angle between the velocity vector and magnetic field is 0 or 180, so in this case charge will be moving parallel to magnetic field lines and there will be 0 magnetic force, and no magnetic force acts on the charge. What if the angle is inclined? So I'll give an angle, random angle, 30 degrees. If charge is moving with an angle of 30 degrees with magnetic lines, we are going to write simple. So angle is 1 over 2. So in this case, magnetic force will be half of the maximum force. The maximum force Q will be. So in this case, magnetic force acting on the charge will be 1/2 of the maximum magnetic force. So for force acting on a charge, which is maximum for 30 degrees, it is 1/2 of the magnetic force, maximum magnetic force acting on the charged particle. And of course, we should know the direction. Direction is also force is a vector quantity. We are going to find the direction of the magnetic field. We will use again right hand rule. And B will be represented by these four fingers. Four fingers are representing the magnetic field lines. Thumb is going to represent the direction of the motion of the charged particle. So, and in this case, palm will point magnetic force acting on a positive charge. But if the charge is negative, moving inside a magnetic field, so opposite of your palm represent the magnetic force acting on the negative charge. But if you take them, you will see that this F is perpendicular to both P and V. So magnetic force is always perpendicular to B, magnetic force is always perpendicular to V, which means if magnetic field is in horizontal plane, force must be in vertical. If magnetic field is in vertical, force must be in horizontal. If velocity is in horizontal, force must be in vertical. If velocity is in vertical, force must be in horizontal, and so on. So magnetic force is always perpendicular to magnetic field. Magnetic force is always perpendicular to direction of velocity vector or direction of the motion. And calculations are not so hard. You can do it on your own. And if a particle is moving inside a magnetic field, so this particle will follow a circular path. If charge's initial velocity is perpendicular to 90 degrees to the magnetic field, the magnetic force acts perpendicular to the direction of the motion of the charged particle. So it is moving like this, but force is acting perpendicular. It is moving like this, acting perpendicular. For that reason, this particle will start following a circular path because this magnetic force acts as a centripetal force. Centripetal particle follow circular path. It is many times asked, several times asked. If a charge is perpendicular to the magnetic field, particle moves on a circular path, and magnetic force acts as a centripetal force for this charged particle. This direction of the circular path can be counterclockwise or clockwise, depending on two things: direction of the magnetic field and sign of the charge. A charge follows clockwise or counterclockwise circle depending on direction of the magnetic field and sign of the charge. So if circle is counterclockwise, the charge particle follows counterclockwise circle. In this case, direction of the magnetic field must be out of the page, and sign of the charge must be negative, or direction of the magnetic field must be into the page and sign must be positive. Positive charge inside a magnetic field into the page, negative charge inside a magnetic field out of the page always follows a counterclockwise circular path like this. But if charge is positive and magnetic field is out of the page, if charge is negative and magnetic field is into the page, in this case, this charge will follow clockwise circles, And this table is very important. All right. So then, if the charged particle is not moving perpendicular to the magnetic field, if it makes some angle to the magnetic field lines like this one, this charged particle is moving at some angle to the magnetic field lines. In this case, velocity has two components. One component is parallel to the magnetic field lines. Second component is perpendicular to magnetic field lines. So parallel component is not affected by magnetic field because remember, if the velocity vector is parallel to magnetic field lines, so no force acts on it. But perpendicular component is the cause this particle to follow on a circular path. So which means this charged particle will follow a circular path, but by the time it will be carried along the magnetic field lines. So it's going to be like this. It will move a circular path, but by the time it will be carried along the magnetic field line. As a result of these two components, charged particle follows a helical path whose axis is parallel to magnetic field. So this is called the helical path. As you see, when particle enters inside this magnetic field, by some angles to the magnetic field lines, it will start moving along the magnetic field by following a helical path. And direction of the axis of the helical path, it is this, will be same direction of the magnetic field. And what about the wire? If it is not a charge, if it is a wire inside a magnetic field, what will happen? So when a charge is at an angle of theta, moves to the magnetic field lines, there will be a magnetic force acting on the charge, QV sine theta. But if you put a wire inside a magnetic field at some angle of theta, so electric current makes an angle with the magnetic field lines. These two cases are very similar. So B and B. Q is I. V is L sine theta sine theta. Magnetic force acting on this wire is BIL sine theta. Theta is again angle between the wire and also current and magnetic field lines. According to this angle, again, there will be sometimes magnetic force maximum, sometimes magnetic force is zero. So if the wire is perpendicular to magnetic field lines, and if the current is perpendicular to the magnetic field lines, sine 90 is 1, maximum magnetic force acts on the wire. But if wire is parallel to the magnetic field lines, like electric current is in the same direction of the magnetic field, or electric current is in the opposite direction of the magnetic field. Yani when angle is 0, or when this case, or when angle is 180, that case. So sine 180 and sine 0 is 0. That's why magnetic force acting on a wire which is parallel to the magnetic field lines is 0. The same, almost the same for the charges, because electric current is also as a result of that charge which is moving inside a conductor. And direction of the electric current is again defined by right hand rule. So we assume that electric current direction is chosen as the motion of uh, direction of motion of positive charges. So if the positive charges are moving like this, which means we say that electric current is also moving like this. That's why palm is going to show the direction of the magnetic force acting on the wire. Because remember, when we are talking about the charged particle, we assume that magnetic field lines are four fingers are representing magnetic field lines. Thumb is representing the direction of the velocity of the particle, also direction of the electric current. Palm was the force acting on positive charge. Also, palm is pointing the force acting on the electric current carrying wire. So it is the same as the positive charge given in the previous title. And next step is, if right here we used external magnetic fields. Here was an external magnetic field. We didn't know about the cause. It could be a magnet, it could be earth magnetic field, it could be some other sources, and we located a current carrying wire inside a magnetic field. But here we have two wires, two parallel wires. So if two parallel wires carry currents in the same direction, these two wires will attract each other with a force equal in magnitude, opposite in direction, acting on different wires. So these two forces are action-reaction pairs. But if two wires carry currents in opposite direction, one of them is up to the plane of the page, the other one is down to the plane of the page, these two wires will repel each other with forces equal in magnitude again opposite in direction, again acts on different wires because action-reaction pairs. But why? How can attract each? How can they attract each other? How can they repel each other? So when each wire is, the key idea is this: each wire is inside the magnetic field of the other wire. So second wire is inside the magnetic field of the first one. First wire is inside the magnetic field of the second one. So does each wire experience a magnetic force due to the magnetic field of other wire? For example, due to the magnetic field of the first wire, because it carries a current, produces a magnetic field here on wire 2. Due to the magnetic field of the wire 1 on wire 2 experiences a magnetic force. So by right-hand rule, I can get what is direction of the magnetic field of wire 1 at the location of wire 2. So the thumb is pointing up to the plane of the page. Curled forefinger on the left side of the wire 1 is into the page. So here, this wire here produces a magnetic field which is into the page. And this magnetic field and this current, which is up to the plane of the page, interacts. this magnetic field because of wire 1 and this electric current because of wire 2 interacts with one another and produces a magnetic field which is to the left. So you can also find the direction of the force by right hand rule. Thumb is pointing up to the plane of the page. Magnetic field forefinger is pointing into the page. Palm must point to the left. So it is the force acting on the second wire. So then, because this magnetic field and that current interacts, equation for the force will be written from these three quantities. B1, I2, and L2 will be equal to F2. Yeah, and F2 is equal to B1, I2, and L2. But for other wire, it's same way, but in opposite manner, like this. Due to the magnetic field of I2, wire 2 makes a magnetic field here. Wire 1 experience a magnetic force. How? Wire 2, if you apply the right hand rule, so electric current is up to the plane of the page, thumb must show up to the plane of the page. Curled forefinger right here will point out of the page, which is dot. So here, magnetic field because of wire 2 will be out of the page. And this magnetic field out of the page here and current of wire 1, which is I1, which is up to the plane of the page, and length L1. These three quantity again interacts and then forms a force to the right. If you use your right hand, you can find it. And B2 multiplied by I1 multiplied by I2 is equal to F1. So F1 is because of magnetic field B2, electric current of I1, and length of L1. Okay, this is the standard test prep. It is explaining this side. That's why I'm going to skip that. And last title of this section is about the galvanometers. Galvanometers are very thin coil that can rotate in a magnetic field when current passes through it, because this coil is located inside the magnetic field, external magnetic field. There is an N pole and S pole of magnet. Magnetic field lines are from N to S. They flow or they go. But when you locate this coil inside the magnetic field and give electric current, so this coil will start rotating. The coil able to rotate about an axis, this is the axis, between N pole and S pole of an external magnet. So this galvanometer, this coil, can measure very small currents from microampere to milliampere, or it can measure very small potential difference from microvolt to millivolt. But if you give some current to this coil, and this coil will start rotating because magnetic force will act on this coil. Here is one coil which is electric current is out of the page, on the other side into the page. So when current passes through the coil, a magnetic force acts on the coil. So this magnetic force produces a torque about this point. So this force, one force according to this figure, if I apply that, so it is on the right side, forces acting downwards, on the left side, upwards. So these two forces in opposite direction causes this coil to start rotating. So the coil starts rotating. And then as coil is rotating, this pointer also starts rotating on the scale. The pointer, yani needle, is attached to the coil, so it also rotates together with the coil. If more current passes through the coil, more force is produced. Each force produces more torque. If the torque is greater, the coil rotates more. So we can, by this manner, we can measure the amount of the current depending on the deflection of the needle on the scale. And this is a video about how a galvanometer works. Let's see it quickly. As I explained, there are two external magnets with N pole and S pole, and a coil. This is the coil you see wound around the cylinder. It can rotate together with the pointer, and yeah, this is the coil. There's a spring, because the spring, when it goes to it, spring causes it to go back, come back again. So when electric current is given, so then this coil, some force will act on this coil, these coils. Now switch is on. And electric current flows through this coil inside this magnetic field from N to S. This coil starts to rotate because of the magnetic force produces a torque about this point. Pointer points, I mean the number on the scale depending on how much current passes on this coil. And this is the symbol of a galvanometer, and then when you connect this galvanometer to a electric current, this galvanometer, this coil gets a current which is Ig, and potential difference across the coil is, or galvanometer, is represented by Vg, and resistance of the coil or resistance of the galvanometer represented by Rg. According to Ohm's law, so these three quantities are related. V is equal to I times R, which means potential difference across the galvanometer Vg, and is equal to electric current across the galvanometer, which is Ig, multiplied by resistance of the coil or galvanometer, Rg. But this galvanometer measures very small current, as I said, from microampere to the milliampere. To use this galvanometer as a volt ammeter to measure the electric current, higher electric current, we should connect a low value resistor in parallel. A galvanometer is converted into ammeter, which can measure very big currents. So ammeters can measure very big currents. But to do that, we should connect a low value resistor, which is named as shunt, in parallel. This is called parallel combination with the coil. So what does this shunt do? When very big current is given to the, is measured, this shunt draws most of this main current. So then, say that here is the 10 ampere is coming, almost 9 ampere is passing through the shunt, but 1 ampere is passing through the coil. So that by this way you can keep this coil safe, because this coil is very thin. If you give so much current to this coil, it will burn. So this shunt draws most of the main current, which is I shunt, and very small current Ig passes through the coil or galvanometer. According to laws of the current in parallel, this I must be equal to Ig plus Is. And because galvanometer and shunt are connected in parallel, their potential differences are equal. Yani Vg, potential difference across the galvanometer, and potential difference across the shunt must be equal to each other. So by using these two equations, we can find what must be the resistance of the shunt to use this galvanometer as an ammeter. An example. We want to use an ammeter of internal resistance 5 ohm. So this galvanometer has an internal, when it says internal resistance, it's talking about the coil. So its in resistance is 5 ohm, Rg is 5 ohm. To measure electric current intensity up to 10 ampere. So we will measure a current, very big current, which is 10 ampere. I is equal to 10 ampere. While ammeter measures a current between 0 and 1. But however, this coil can measure maximum 1 ampere. So your Ig current of the galvanometer will be maximum 1 ampere. What is the resistance of the shunt that should be connected in parallel with ammeter in order to do this job? So 10 ampere is coming from 10 ampere main current is coming, but only 1 ampere must pass through the coil, which means 9 ampere must pass through the shunt. So the electric current on the shunt must be 9 ampere, which is 10 minus 1, which is 1. And after that, you are going to use the potentials, equal potentials on the coil or galvanometer and the shunt. So which means I shunt times R shunt must be equal to IG times RG. So I shunt is 9 ampere, we got it. R shunt, what is the resistance of the shunt? We will find that. Galvanometer measures maximum 1 ampere and resistance of the galvanometer is 5 ohm, 1 times 5. So if we divide by 9 over both sides of this equation, we got the shunt as 0.55 ohm. And then this galvanometer also can be converted to a voltmeter, which can measure very big potential difference. But to do that, we are going to use a high value resistor this time, and also connect it in series with the coil like this. So in series combination, electric currents are equal. So electric current through the galvanometer and electric current through this resistor must be equal. And when you connected this resistor in series with the galvanometer, this resistor, most of the total potential difference V is drops on this resistor. A very small potential difference remains for the coil or for the galvanometer. According to laws of potential difference, Vg plus Vr must be equal to V. And according to law of currents in series, because currents are equal, so Vg over Rg, which is current on galvanometer, must be equal Vs over Is or Vr over R on the resistor. And one problem about this, so question says that a moving coil voltmeter measures potential difference between 0 and 5. This coil can measure maximum 5 volt, and potential difference across this coil must be maximum 5. If the resistance of the voltmeter is 500 ohm, if the resistance Rg is 500 ohm, calculate the intensity of the current through it if it reaches 5 volt. If Vg is 5, if Rg is 500, it's easy to get Ig by Ohm's law. Ig is equal to Vg over Rg, which is equal to 5 over 500, 0.01 ampere. So which means this coil can carry only a current which is 0.01. This current mustn't be greater than 0.01. So we will use this 0.01 for the second part of this problem. Second part says that we want to use this voltmeter to measure a potential difference greater than 5 volt. What is the resistance of the resistance that should be connected in series with the voltmeter in order to measure a total potential difference of 30 volt? So I will do for 30 volt. Yeah, and total potential difference V will be 30, but we know that this galvanometer can measure maximum 5, so not more than 5. So if this is 30, if 5 must drop on Vg, which means potential difference across the resistor must be 25, because 25 plus 5 is going to be 30. So I will get first what is the potential difference, what potential difference must drop on the resistor. So 30 total potential difference is equal to 5 plus Vr, so Vr is equal to 30 minus 5, which is 25. Next step is use Ohm's law. What? Electric current on the resistor, on the galvanometer, and electric on the resistor must be equal. We got the electric on the galvanometer, which is 0.01 ampere. So electric on the resistor also must be 0.01. So I will use this current to get R, because we know Ohm's law, R is equal to VR over IR. VR is calculated at 25, and I can be maximum 0.01, 25 over 0.01, which is 2,500 ohm for this question. And the last title is the loudspeaker. Loudspeakers are the devices which converts electric signal into sound. It's opposite of a microphone. Microphone is converting sound to electric signal. Loudspeaker is converting the sound electric signal to the sound. So the electric signal is a sound wave is converted to a very electric signal by a microphone. After that, this electric signal is amplified, which means power increase, and sent to the loudspeaker. This varying electrical current causes a very magnetic force on the coil of this loudspeaker, and this alternating force on the coil causes vibration of the attached cone, which produces the variation of the density of the air in front of it. So a loudspeaker basically has 4 components. One component is a permanent magnet. Second one is a coil. Third one is a cone. Fourth one is a frame which keeps all those things. So when electric current is given to the coil, this coil starting to vibrate between the magnetic field, and then this vibration, because coin is connected to this coil, so coin is also vibrating, and this vibration later is converted to the sound or vibration of the air molecules, which is producing the sound in the room or in the environment. So this is all about this section 3. And one more last device we have, which is about magnetic resonance imaging, which is inside story. MRI machines are using magnetic field. We should know that they use very strong magnetic field to image the human body or even the to human brain. It's a very good technique. Magnetic field, with this strong magnetic field produced by big electric currents, are interacting with the human body, the water molecules in the human body, and then you can get image by this way. They are used for imaging the brain. So as you see, you can get very clear image of the brain and the spinal tissues. And they are also used to study brain functions, brain tumors, to get the image of blood vessels, which is useful for studying circulatory system. So we should know that where they are used, it is better. But how? Magnetic field is external magnetic field, strong magnetic field produced by strong current, interacts with the water molecules in human body, and then it forms, by this technique, we form an image on a screen. Okay, this is all about section 3, and then tomorrow we will do chapter 6, section 1 and 2 only tomorrow. Next day only section 3, 6.3 will be started. Evet, bugünlük bu kadar. Katıldığınız için teşekkürler. Yarın görüşmek üzere.
Teşekkürler hocam.
Evet,
Güle güle.
görüşürüz.